Hey everybody, it's Tuesday, May 18th, and as you can see here in the aim for today, our goal for today's video is to talk about how electromagnets and generators reveal the deeper connections between electricity and magnetism. So we have spent the last bunch of weeks talking about electricity. Since the middle of last week, we started to talk about magnetism. One of the most important ideas in physics is that electricity and magnetism are very closely related. In fact, oftentimes we say electricity and magnetism are like two sides of the same coin. And so what we really want to establish in today's video is how the two things are related. And we already have gotten to this a little bit so far because we saw last week that magnetism comes from the charged particles that make up all materials. We said so far that every single electron basically behaves as though it has a tiny little magnet in it. And the main point of that discussion was to show that in certain materials we generally call ferrous metals, that's why they're able to be affected by magnetic fields. In iron, for example, the reason why iron is able to be magnetized is because it has electrons which have their spins, which is the phenomenon that gives electrons their magnetism, all aligned in the same direction. That's a little too complicated for this class, but on the level of this particular course, this is what you need to know. If an electric charge is stationary, it produces an electric field. That electric field extends out infinitely into space, and of course, the direction of that electric field depends on whether the charge is positive or negative, right? We talked about that when we were talking about static electricity. Positive charges have their electric field lines coming out. Negative charges have their electric field lines coming in. Electric field lines go out of positive charges and go into negative charges. That's the deal. Now, if an electric charge is moving, now this is a different scenario. If an electric charge is moving and it's moving at a constant speed, that electric charge also generates a magnetic field. Now, I want to be very clear about this because maybe the way this is written makes this a little confusing. I want to be clear. I said when a charge is moving at a constant speed, it also generates a magnetic field. So that means it generates a magnetic field and an electric field, which I'm going to abbreviate here as E field. So if the charge is stationary, it generates an electric field. If the charge is moving at a constant speed, it generates a magnetic field and an electric field. And lastly, if a charged particle is accelerating, it generates electromagnetic radiation as well. So I want to be very clear about this. It generates electromagnetic radiation and also E fields and B fields. Remember, the abbreviation for a magnetic field is a B field, B for borealis, because of the way, compass needles always point north, because the Earth has a magnetic field. This slide contains essential information. If an electric charge is stationary, E field only. If it's moving at a constant speed, E field and B field. If it's accelerating, E field, B field, and electromagnetic radiation. That's an important thing for everybody to realize. Take a second to pause this video here and write that down. When you hit play, we'll move on. Now, some questions we can ask to put a bit of a finer point on this, I think will hopefully make this a little easier to understand. So the first question that we'll ask here is, if there is an isolated, insulated region of space with no electric field, how can I introduce an electric field in that region? Let's just basically pretend like we have an isolated and insulated black box, and there's nothing inside that box. If I want to get an electric field inside of that box, how can I do that? The way that I could do that is by putting a charged particle in that region of space. So I wrote here, in order to produce an electric field in the region of space, we must introduce a charged particle to that region of space because charged particles generate electric fields. That's an important point. We can also ask the question, well, if there is an isolated insulated region of space with no magnetic field, how can I introduce a magnetic field in that region? Now, obviously, the answer is, well, I could just put a bar magnet. That's true. But what you can also do is you could introduce a moving charged particle, since moving charged particles generate magnetic fields. This is super, super important for you to understand. Take a second to pause this video here and write that down. You don't necessarily need to write down the 2 questions, but you should write down the answers, the parts here which are not written in bold. And when you hit play, we'll move on. Now, of course, the obvious question here is, well, why does a charged particle just produce an electric field, but if it's moving, it all of a sudden produces a magnetic field as well? The basic answer to this question is that there is a very important concept in physics known as electromagnetic induction. And electromagnetic induction is essentially a concept which describes the relationship between electricity and magnetism. And electromagnetic induction really is a concept that says 2 very simple things. It says a changing electric field will produce a magnetic field, and it says a changing magnetic field will produce an electric field. This is just a fact. These are, well, really, they're 2 facts, and these are 2 facts that you absolutely need to know. So take a second to pause this video here and write that down, and when you hit play, we'll see how these concepts can be applied to explain how an electromagnet and a generator work. All right, so the first note here is a changing electric field will produce a changing magnetic field, or produce a magnetic field. Now, first, we should ask why that makes sense. And I think it makes a pretty good amount of sense if you just consider what the electric field of an electron looks like. So remember, electric field lines come out of positive charges and they go into negative charges. And so this is what the electric field looks like. Sorry, my pen is acting up here. This is what an electric field looks like for a negative charge. It goes out in every direction, right? The lines extend infinitely off into space. We don't need to show that here. We could just show a basic arrangement like this. And let's say there's a point in space over here, which we'll label point A. If this electric field has a speed to the right, at this point, because the charge is getting closer and closer together, if somebody was standing here at point A, they would measure the electric field as getting stronger and stronger and stronger, because when you get closer and closer to a charged particle, the field gets stronger. That's the point. Now, because just the motion of the charge in general means that the field is changing for any observer, the motion of the charged particle represents a change in its field. The change in an electric field produces a magnetic field. So these changing fields, I want to write this down here. This would probably be a good note for you to write down. These changing fields generally refer to motion, because the very motion of these objects relative to any observer is going to change the strength of their field, right? If you're moving towards someone, the field is going to get stronger. And if you're moving away from somebody, then the field is going to get weaker. That's the idea. Now, ultimately, the aim for this video sort of hit at an essential point here, which is that the workings of an electromagnet and a generator can be explained by this concept of electromagnetic induction. So let's go ahead and see how that works. The first device we're going to look at is an electromagnet. An electromagnet is basically just a coil of wire through which a current could flow. And the idea here is that when this coil of wire has no current flowing through it, there is no magnetic effect. However, when you turn the electricity on and now you generate a current flowing in this wire, there is a changing electric field. And the changing electric field creates a magnetic field. And that's how the electromagnet works. Now, there's one thing I want to write down here before I show you how this works. The idea is when a current flows through a wire, that represents a changing electric field. The reason it represents a changing electric field is because the moving electrons in the wire bring their electric fields with them. That's a super important thing for you to understand. The reason why a current represents a changing E field is because as a current flows, remember, a current really is just a flow of electrons. As those electrons flow, the field in the wire changes due to the flowing of all these electrons, which are all generating an electric field. That's the idea here. Motion generally represents changing fields. And the basic idea here is that the current represents a bunch of literally trillions of electrons in motion, and so the field would be changing. Now take a second to pause this video here and write that down, and when you hit play, we'll take a look at a simulator which demonstrates this point. Okay, let's take a look at the simulator here. I can post a link for this simulator. It's another PhET simulator, which you can definitely find online. Let's go to the electromagnet portion of this simulator. Now, as you can see here, there's a compass. Now, let's actually just go back to the bar magnet thing for a second. Remember, a compass is a tiny little magnet. And so, as you can see here in this little simulation, the red side of the compass, like is shown here by the red side of the magnet, is a north pole. And so as we move the compass around the magnet, the north pole of this compass is always going to respond to the magnet. When we put it on the side of the magnet with the north pole, notice it is repelled and it goes away, right? Because like poles repel. But when we put it back to the south side, well, it's going to stay oriented this way because opposites attract. That's the basic idea. The main reason why I'm showing you, though, is to remember a compass is a device that detects the presence of a magnetic field. We can tell it is detecting the presence of a magnetic field because of the direction it points. So now we go back to this electromagnet simulator. Notice here, the voltage in this battery is 0. If we show a field meter here in this simulator, notice the magnetic field that this thing is measuring is 0. There's no magnetic field being measured by this device. You can also probably tell in the simulator that the voltage in the battery is 0, and that's why there's no current flowing through the wire, and so there's no changing electric field happening, and so that's why the compass isn't detecting a magnetic field in the wire. Notice the compass is always staying pointing in the same direction. That means it's pointing north. North, geographically, the North Pole, where Santa lives, apparently in this simulator world, is somewhere up here in the corner of the screen. What you hopefully you'll be about to notice here is that this is going to change when we turn the battery on. Watch the little blue dots in the simulator. We turn it on, those blue dots flow. Notice the direction of the compass needle changed almost instantaneously. This thing is pointing up here to the corner of the screen, and then when we turn the current on, it turns around. That's the basic idea, because this thing is detecting the presence of a magnetic field. Notice here, really, all these tiny little compass needles are showing you the direction of the magnetic field. And so the basic idea is, because each of these individual electrons carries its own electric field, and now all of those electrons are moving, this thing is generating a magnetic field. Now, obviously, the reason why electromagnets exist is because the thing about like a permanent magnet is that, well, it's permanent. You can't turn it off. However, an electromagnet can be turned off. Sometimes, if you've ever played with a magnet, you might have noticed that you could stick something to a magnet and then you have a hard time pulling it off. Imagine you were trying to use an electromagnet to pick up a car. The nice thing about that is that if you just turn it off, the car is going to drop. If you use a really strong magnet to attract a car, but it's a permanent magnet, you can't turn it off, you have to pull the car off of the magnet, which is going to be an almost impossible task. The point here is very simple. The way an electromagnet works is that the current flowing through the wire represents a changing electric field, and the changing electric field produces a magnetic field. That's the basic idea. Now, of course, the flip side to this concept, as we mentioned here, was that a changing magnetic field will produce an electric field. And you might be wondering, well, how can we demonstrate that idea? And the device that demonstrates that idea is called a generator. This little diagram shows you essentially what a generator is. Inside of a generator, there are basically coils of wire wrapped around the outside. And the inside of a generator is basically just a permanent magnet. Some sort of fuel powers the generator, and a lot of times it's gasoline, and that burning of this gasoline causes there to be, like some sort of crankshaft that spins. I mean, you guys probably know more about engines than me if you're paying attention in shop. So the idea is the generator burns gas, and obviously all engines involve some sort of rotation. They cause the magnet to rotate, and the rotation of the magnet constitutes a changing field. Remember, we said in this slide over here, changing fields generally correspond to motion. And the changing magnetic field produces an electric field, which, as we said, is generally represented by a current flowing in a wire. So let's go ahead and see how a generator works. So here in this simulator, we also have a tab here that says generator. Before we get to that, I just want to show you this thing that says pickup coil. A pickup coil is basically just a device, a coil of wire wrapped around something that can measure voltage. And whether you want to make that a light bulb or you want to make that a voltmeter, either way, it doesn't really matter. You can see here when there is no motion, the magnetic field is constant. We can even show this here. Notice we set it up and the compass needle points in a fixed direction, and that's it. But when we move the magnet, we change the field. And because we change the field, you can see the compass needle spin, right? We could actually put it over here to show that it's changing. When we pass the magnet through the coil of wire, there's a voltage generated. Look at the compass needle, it's spinning around. It's changing. Now, obviously, because there's a voltage, this is generating some electricity. But you can see it's kind of a weak voltage, and it's not particularly sustained. And this is a pretty idiotic way to generate electricity. We could generate pretty consistent alternating current if we just do this over and over and over and over again, moving the thing back and forth and back and forth and back and forth. But that's not practical. A generator takes care of that for us because it puts the magnet on something that can spin continuously. And I noticed, I just said before, a generator is typically powered by gasoline. That's like one that you would find in a house. In like a big power plant, there are many generators which are powered by falling water. These are called hydroelectric power plants. So notice here in this little version of this simulator here, we could turn the water on. Notice the magnet spins. We can see here from the compass, the magnetic field is definitely changing. And now we see there's a sustained voltage created in this wire. The basic idea is because there is a sustained voltage, there will be a sustained current. The sustained current effectively is electricity. We can also show this here to show the field. Notice these little individual compasses at all these little locations are continuously spinning, and that's because the field is changing. And because the field is changing, we're generating a changing electric field, which of course is represented by the electrons moving in the wire. Now, it should be noted, this is not a direct current. This is what's called an alternating current. Hopefully you learned about that in shop. The basic idea about an alternating current is that the electrons are not all flowing in the same direction. They're basically just flowing back and forth and back and forth. Now, you'll notice if you look at any of the devices you have in your home, this is how most devices work. Basically, the only devices that use direct current are basically devices that you charge, like your phone or your computer. If you look at every single charger you have for those devices, you'll see like a big brick associated with it. And that's basically a transformer, which changes the alternating current coming out of your wall to direct current. My personal computer is a MacBook, so I have a MacBook charger here, and I can just look at it. If you look, it says, and it'll look like this with any computer charger. It says the input is 100 volts or 120 volts, like from a household voltage source. And it says it takes in about 1.5 amps at 50 to 60 hertz. In America, it's 60 hertz. It says the output, on the other hand, is 20.3 volts of DC electricity. And it's a 3 amp current. So that's the basic idea. This thing is going to spit out direct current after receiving alternating current. The reason why your house receives alternating current is because that's how electricity is generated. We use generators just like this to be able to generate electricity. Just to summarize very quickly, the basic idea is that when we have a changing magnetic field, The changing magnetic field produces an electric field. A current flowing through a wire represents that changing electric field because the moving electrons in the wire bring their field with them. Take a second to pause this video here and summarize that. When you hit play, we'll move on. All right, moving on. Now, there's definitely something really, really important we have to talk about with a generator that brings us to really the last topic for this video. And that is pretty simple. We just said a generator creates electricity by, having this changing magnetic field produce a changing electric field, which is a current. And as we just showed with that simulator, the reason why there is a current generated in the wire is because there was a voltage induced in the wire. This is what we refer to as an induced voltage. I want you to write this down. If a changing B field, which remember stands for magnetic field, if a changing B field is inducing a current in a wire, then the changing magnetic field must also be inducing a voltage in a wire, because you cannot get a current without a voltage, right? That goes back to Ohm's law, V equals IR. You cannot get a voltage without a current. So if there is a current, there must be a voltage to go along with it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on here. Let's talk a little bit more about that in a little more detail. We can say here two important things. Key concept. In order for a voltage to be induced in a wire or a conductor, the wire must move in a direction that is perpendicular to the field lines. That is just a fact. What that means is it's just a requirement. It's literally just a fact. It's just something you have to know. A way that we like to say that in physics is that the wire has to cut the field lines. An easy way that we can show this is by taking the fingers of our hand and pointing them in a particular direction. If you're looking at a screen right now, like on a computer, I want you to take your fingers and point them into the computer, like into the screen. So your four fingers should be facing away from you towards your screen. And I want you to take the index finger of your other hand and put it in between your middle finger and your ring finger. So literally in between those two fingers. If you move your finger up and down, you are not cutting the field lines. You are basically, imagine if your finger was a knife, you'd be like cutting your fingers off. If you move it away from you or toward you, you're not cutting your fingers off. The only way you can move your finger if it is pointing straight up and the fingers of your other hand are pointing straight into your computer screen is if you move them left and right. That would be cutting your fingers, or in other words, because your fingers are representing a magnetic field, cutting the field lines. That's an important thing to realize. Now, as we mentioned, it's motion that causes changing fields in the first place. So since the motion of the wire causes the voltage to be induced in the first place, when the wire is moving at a larger speed, there will be a larger voltage induced in the wire. I understand it might be annoying that these things might not seem obvious, but at the end of the day, they are just facts that we've determined from experimentation. So they're just things you need to know. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so let's show what we mean here. Here's a nice little diagram that helps to make this a little clearer, I think. It says there is no current induced when the movement of the wire does not cut through the magnetic field lines. Look at the magnetic field lines in this diagram. They go from north to south. If we take the fingers of, let's just say your left hand, point them to the right, make sure your palm is facing you to make this make a little more sense. Notice, if you move your fingers into or out of the screen, like in that direction, toward you or away from you, you will not cut the field lines. If you move your finger to the left, that means toward the North Pole or toward the South Pole of the magnet, you do not cut the field lines. You only cut the field lines when you move up and down. That's an important thing to realize. Now notice in this particular diagram, they've shown a north and a south pole of a magnet. They don't always do that. What they often show in these kinds of problems is a diagram with X's and O's. So I just want you to write this down here quickly before we move on to some problems and wrap this up for today. Magnetic field diagrams can be used to show the direction of a magnetic field. If the diagrams are marked with an X, this means into the page. That's an important thing to realize. If the diagram is marked with an X, that means into the page. You know how I used to remember this when I was in school? If you take an X and you rotate it a little bit, it looks like a T, which is in the word into. If the diagrams are marked with an O, this means the magnetic field is out of the page, and that one is pretty self-explanatory, right? The O stands for out. Take a second to pause this video here and write that down, and when you hit play, take a look at a problem. All right, let's take a look at a problem. This problem is in the review book, which you don't have, but it is in the review book nonetheless, which is on page 141. It's number 43. It says, in the diagram below, a straight wire is at rest in a uniform magnetic field directed into the page. A potential difference, or voltage, will be induced in the wire if it is moved. Choice 1, toward the top of the page. Choice 2, toward the right of the page. Choice 3, into the page. Choice 4, out of the page. Take a second to pause this video and try this out. See what you think. And when you hit play, we'll go over it. All right, now I thought they were a little generous in this problem by telling you the magnetic field is directed into the page, but notice there are X's there. So that tells you the magnetic field is directed into the page. The easiest way to answer this is to take your hand and point it at your screen. Then you could take the finger of your other hand and hold it where the wire is shown. Notice if you move the wire towards the top of the page, you are not cutting across these field lines. If you move it into the page, you are not cutting across these field lines. If you move it out of the page, you are not cutting across these field lines. The only direction of motion that will be shown to cut across the field lines is if you move it towards the right, because if it goes towards the right, it will cut the field lines. That's an important idea. Take a second to pause this video here and summarize the answer to this question, and when you hit play, we'll move on. All right, moving on. Last question for today. When an electron moving in a magnetic field experiences a magnetic force, the angle between the force on the electron and the lines of flux, or in other words, the magnetic field lines, is always 0, 45, 90, or 180 degrees. Nice little challenge question. Take a second to pause this video here, answer this question, think about the answer, think about why the answer is what it is, and when you hit play, we'll move on. All right, now hopefully you realized that cutting the field lines means if the field lines, let's say, are pointing in this direction, if you want to cut them, you would not slice this way or like out of the page or into the page. You have to slice this way to cut that arrow in half. Do you see it? It has to be at 90 degrees. The basic idea is everything that is involved in translating electricity to magnetism is all about the things being perpendicular. At the end of the day, this is just a fact we have learned from experimentation. The wire or conductor is just a collection of electrons. And in order to feel a magnetic force, to get that induced voltage, to get that induced current, it's got to be perpendicular to the field lines or cuts the field lines. And so basically, in any kind of magnetism question, if they ask you when an electron is going to feel a force from a magnet, or which way do you have to move a wire, which way does the electron have to go, the answer is going to be 90 degrees. The basic ideas in this video can be summarized in about 1 minute. Magnetism causes electricity. Electricity causes magnetism. If there is a changing electric field, that electric field will produce a magnetic field. If there is a changing magnetic field, that will produce an electric field. In order for that to happen, there needs to be motion, because the motion represents the changing of the fields. An electromagnet is basically a device that operates according to the first principle. A changing electric field produces a changing magnetic field. That's why the current flowing in the wire that makes up the electromagnet will produce a magnetic field. And a generator represents the flip side of that, that a changing magnetic field produces a changing electric field. That's why the spinning of a magnet will create a current. The last thing that we said here, which is very important, is that if there is a current created from a changing magnetic field, then it must also create a voltage, which can only happen when these objects, like a wire in a magnetic field or an electron in a magnetic field, move perpendicular to one another. If things are moving perpendicular to one another, that means they're 90 degrees apart. That means field lines, as we say, are being cut. And with that, that's it for today. Tomorrow's assignment will require you to put all this to the test. Have a good one, everybody.